Right. Hello, everyone. Thanks for tuning in. So my name is Bahareh Tolooshams. I'm an assistant professor at the University of Alberta and also an Amii fellow. So today we're going to talk about interpretability in AI. So if you don't know about interpretability, so this is a time to learn a little bit more about it and why it's useful in the age of AI and technology. All right, so we have been all perhaps observing the rapidly growing capabilities of artificial intelligence. So here is an example of how that gave us physical AI robotics, an example from Boston Dynamics, probably from several years ago, all the way to how generative AI is being used in drug discovery to give us proteins that we could not design in a short period of time as scientists, all the way to perhaps they're going to tell us what kind of disease we're going to have in 20 years. I can talk about this maybe for hours and hours, all the way to maybe we hear in the news that they're doing better than human in trying to spotting bone fractures in the medical field. And the case of large language models are one that we probably tend to, it's impossible for us not to mention it when we talk about AI these days. However, all these wonderful intelligent systems, they still make mistakes. So an example that these robots may fail drastically when you expect the least. Some other examples are where we are trying to use generative AI to give us a molecular structure, but all it's producing are combinations of molecules that are not even valid scientifically, so they are non-existent, to when they're so confident when they give you a wrong answer. And I can again talk about all the problems that they have. At the same time, they have promising performance, to even though they have jaw-dropping performance and high accuracy, we're still afraid to use them in high-stake applications because maybe they fail 10% of the time, but that 10% of the time is going to cost us a lot. So with my mindset of academic, and I do like to make abstractions, so let us classify these challenges. Of course, there are more challenges. That's why I say a few challenges here. So let us have a classifications of a few of these challenges of modern AI systems. So they're not reliable, so they unexpectedly fail. It's hard for us to take them from one hospital to another, from one country to another, from one scenario to another situations, and to be able to rely on them to work well. So they're sensitive to these new situations, what I can call it. But the other two that I take interest, and you're going to hear more about it today, is indeed in the particular regime of these AI frameworks that are their black box property. Their decision processes are hidden. We're not fully aware of their internal reasoning. And getting back to that molecular generation that I told you about, the validity of their outputs is what appears as an obstacle in making AI to have a real impact on certain scientific or engineering application. So in the case of the validity, as I mentioned, they're confidently wrong about their answers, but more importantly, they're giving you outputs that are inconsistent, maybe with our physical world. So today I'm going to focus a little bit about science. I'm an engineer that likes to talk about science, so let's have that in mind when you're listening for the next hour, that what makes an intelligent system useful for scientific domains. If you're an engineer, think about it, what makes an AI system useful for engineering applications. There are two that I'm pointing out here, so we want them to be reliable and collaborative. So I'm not going to go to the details of those, but the other two that make interest for me for today's session is we want them to be understandable. And what I mean by that is we want to have a transparent reasoning. We want to have an idea of how they come up with their decisions and what are the factors that they rely on to give us the decisions and the output if it's a prediction task or maybe diagnosing a particular person with a cancer or tumor. And the other one is the systems to be grounded in reality. So how you can understand that is the case of you want these frameworks in the same way that maybe a lot of our classical algorithms work or the way your reasoning works. We want these frameworks ideally to respect the underlying causal, if it's a physics system, physical, if it's a biological system, biological processing that govern your data that you're studying. So let's focus on the understandable and grounded reality with me. All right. So why do we need these? So perhaps I might be within the minority in this room, or maybe within the whole 4 days of the conference to talk about interpretability. A lot of people talking about improving performance, reliability, agentic AI, and all the good things that are happening, but we tend to not put a lot of focus on interpretability. And hopefully, I'm going to show you a perspective why we need them. And here is an example for science. Why do we need interpretability? Because the range of the questions that we ask are not on decoding or are not on an accuracy of a particular task. They're more onto the field of we want to understand how the brain works. So focus on the first word. We want to understand. Or we want to understand how does the brain represent our world within its neural activities. If you're a physicist in the room, you can translate these questions to your own scientific questions about the world. So maybe you're trying to model a black hole or dark matter, and you may ask some questions on understanding to enhance our understanding about those. But let me get back to neuroscience. So I give you an example of a problem in neuroscience to see how interpretability is useful in that region. So we have an environment, and there are certain variables that are going to interact with the system that we want to study. So in this case, it's the brain. Imagine that there is a mice that is moving around in the environment, and there are certain things in the environment that we are calling that stimuli that stimulate the brain of that animal. So maybe you give water to it, maybe it sees a friend, maybe it sees a threat. So all of those are going to interact with that system that is under study, and it gives us some measurements, the data. So these can have different form. It can all the way come from pointing implant electrodes into the brain to get single neuron activities, or it can be a cap of EEGs, or it can be MRIs or functional ultrasound. So let's refer to them as data. So given those data and measurements, the job of the neuroscientist is to gain understanding about the system, or if I want to say it a little bit more academically or scientifically, to uncover the generative process that underline the data. And that uncovering that generative process relates to what are the causal factors that have stimulated the brain, and that can tell us how the brain works. So there were nothing about numbers. So I don't think you're actually going to see any number today. So it was all about understanding. All right, so what I'm trying to argue here is if you want to really use AI for the benefit of scientific discovery, if an AI system for you going to do a prediction, doing the task of the prediction without understanding is going to be useless. or let's say not so useful, because that's a quite bold statement that I'm making here. I'm sure there are a lot of people that disagree with me. But sometimes you have to simplify statements to be able to connect to the audience. So let's say not so useful for science. So, and then in order to make the AI system useful, there are two types of questions that you can ask. One that is on the screen. Let's say you have an AI system that is already working properly. So we want to understand, how can we understand what the AI model learned? Or we want to say, is that AI system really truly understand what it's doing? So understanding the world. A lot of understanding. So, and to tackle these questions, if you were to indeed provide an answer to these two questions, is one of the key that remove obstacles for us to be able to do scientific discovery. So if you're interested to know a little bit more about how predictions without understanding may not be very much useful for science, I refer you to this really nice NeuroView paper. All right. Okay. So I talked a lot about understanding. The title of the talk was Interpretability, but we actually still don't really know what it really means. So let's take a look at it together. So as a non-native speaker, I'm not an English speaker, let's look at the dictionary, and what you find in terms of the word interpret. It means that you want to explain or to present in understandable term, and I add a human to it. So the human, in a case of that you want the AI to be able to add and give you some understanding. And why do we need interpretability? Because if you actually even go more into the academic literature, in the psychology, explanations may highlight an incompleteness about the system that you're studying. And how that can incompleteness look like? So it can basically have all the desirable properties that you're interested in tackling and addressing in your system. So interpreting your model can give you insight that your AI framework is not fair, your AI framework doesn't rely on causal information, your AI framework is not reliable, and you can go on. So I know the texts are quite small, but there's a really nice paper that came early years when at the academic institution we start talking about interpretability in 2017. So I encourage you to take a look if you're interested to know about this more. All right. So what are we going to do today? We're going to talk about two forms of interpretability. So one is on, we want to interpret the AI, and that field nowadays most of the time referred to as mechanistic interpretability, in a way that, for example, we have a language model, it's already trained, so you train your data, and now you're trying to understand and analyze it post hoc. So I do call it, you understand the AI. And an important information or factor here is that this field of interpretability, at least at the base level, is not going to resolve the challenges of the AI system relying on wrong reasoning, or AI system is being not robust or harmful. But because of those highlight of an incompleteness, of course, we can use that information maybe to mitigate harmful behavior. So this is an important thing that I would like you to take away from this slide. Okay, so the other form is what I refer to as interpretable AI. So what does this stand for? It's basically that blue left bottom part of this slide for what makes science useful in a way that we are looking for models that are grounded in reality. You can think about it in a way that you want the AI system to be aligned with the world, or if the world is you, to be aligned with how you're thinking about problems. So in other words, to respecting the laws of the nature. So if you're, for example, trying to analyze a biological data, there are certain biological properties that exist in your experiments. Maybe there is a particle interactions, if it's molecule binding, there's some energy levels, or maybe there's some molecules that never go together. So you want your system to respect these properties. All right, so let's focus first on the first part. We're going to get to the second part as well. Don't worry if you want to hear about the second one. Okay. So what are the few questions that might be useful for us to ask? So maybe you would like to know how the AI system come with their decision. So the field of the mechanistic interpretability is trying to look into the internal activations of, let me call it, large models. It shouldn't necessarily be a language model. To try to either reverse engineer the role of the network component or identify some of the components that are having an impact on the decision. Again, there are two papers at the back, at the bottom of the screen, if you would like to know more about this field. Another one, probably this, you're not trying to look for how do they come up with their decision. So imagine that you train a large foundation model on trying to predict how a planet moves around in a solar system around the sun. And you generate almost close to infinite amount of data, so let's say large amount of data, enough for it to do a perfect prediction, as we're showing here, to be able to predict you how well it's moving. And then the question that you ask is, what is a world model? What is that understanding of this system about the task that it's performing, about the prediction that it does, that this is how a planet should move around the sun? Do they have the same understanding? For example, we know about the Newtonian law. Can we actually extract what is that laws of nature that they're relying on? Does that align with how we know how planets should move? So these are type of questions you can ask. Again, as you see, we're not trying to, at the first level, resolve their deficiencies or the fact that they're making a mistake. We're trying to understand them. Okay, so let's take a close look to the mechanistic interpretability part. So this field tries to understand how does large neural networks represent the data. And if we have access to that model, you can think about it that the task that we are going to do is that we take the internal activations of that large model and try to decompose that activation into some interpretable component. So that interpretable that I mentioned, again, it's under discussion. A lot of people says, how do you define interpretability? But let's for now accept the fact that we have models for us to be able to decompose these activations into component that we understand. All right. So in industry, this field of mechanistic interpretability started, I think, around 2022. And since then, there are a variety of techniques that have been proposed to be able to provide you, for example, with these visualizations of the geometric representations that are inside language models. So here I bring 3 examples. So if you were to take a look into one of the recent the latest machine learning conference of iClear, there are even more and more results coming. So these are from last year that I'm showing. So if your foundation model is trained on biological data, so they show that it seems they have captured some tree of life. The foundation model, in this case, a language model, has come up with some geometric representation that help them to do accounting tasks, and we can move on and on. But let's actually understand how these are being achieved. All right, so let's get a little bit more abstract here. So how this field started. Some people sat down and tried to hypothesize about how the semantic information, concepts that exist in our world, at least in our understanding about the world, are being encoded in neural networks. So in this particular example, so let's say we have three concepts: a concept of a cat, concept of a car, concept of a table. And these concepts can actually be very, very, very large number. The set can be extremely large. But the key is the fact that even though language models have increased in size dramatically, the number of neurons that they have, it's still much, much less than the number of features that exist in our world semantically that we want them to be able to represent. So in this simplistic example, we have three concepts, and we want to move to two neurons, two computational neurons. So, and what they hypothesized is the fact that if these concepts are not really going to co-activate most of the time at the same time, we should be able to use one neuron, for example, to represent two of them. So assign features that rarely co-occur to one neuron. And this concept is known as a superposition. And as the sparsity of these co-activations increases, you should be able to fit and encode more concepts with less number of units, which I'm referring to as neural networks. So this field basically brought us to what is known as sparse autoencoders. So with this hypothetical, with this hypothesis about how large language models or neural networks are incorporating information, we say, okay, let's construct a sparse autoencoder. What is it going to do? I'm going to take an internal activation of my model as the input, and I'm going to pass it through a simple encoder to map it to a high-dimensional sparse representation, which you can think about it that we are going from the right side of the screen to the left side in the encoder. So this is why the encoder is high-dimensional and sparse, such that now if you look into each of the elements to this activation, there's going to be a disentanglement of those concepts that were entangled in your language model. So you train this, and let's not go through all the details. I can talk about the details of what makes sparse autoencoders powerful, what are their limitations, or how they should be designed, depending on what structures you want to infer, you want to extract. All right. So now you can take a sparse autoencoders, let's call it an SAE, so that it will be easier for me to spell it out. And thinking about what type of structures you want to extract from your language model. So it shouldn't necessarily be a language model. Again, like it can be a large foundation model trained on biology. If you were to, for example, be in the A scenario, so maybe you hypothesize that your concepts are linearly accessible and they're taking this orthogonal direction, you can design one type of SAE. If you were to hypothesize that the concepts that are inside my large neural network take some form of hierarchical structures, you can design another form of SAEs, and you can move on and repeat the same process. So I want to make an important note here is the fact that majority, till maybe probably last year, majority of the literature on sparse autoencoders were operating in the A scenario, where they were taking an orthogonal, linearly accessible concepts. And indeed, last year, we tried to extend this to extracting more richer form of representation. And since then, there are a lot of interesting works that are coming out. All right. So let's take a look into what type of structures we can get. And if we were to look for hierarchical representations to learn from language models or large vision models, what it can give us. So this was a joint work that I had the privilege to work with 4 researchers. Valerie is here. You should be able to find her in the app and talk to her. The one in the top left, it's a collaboration with Harvard University. All right, so what do we do here? So why do we need hierarchical structure? So think about it as following. So if you're a language expert, probably you should be up here to talk about this, but let me say it in simple words as I understand. So we can think about that we have a tree of structures that is hierarchical in a way that instead of trying to represent your data in a quasi-orthogonal, in a way that you have one direction for birds, one direction for fish, one direction for mammals. So maybe you want the concepts that you extract to have some form of conditional orthogonality, which basically means you go a sequence of hierarchical concepts to learn. So as an example, so maybe you want to learn or extract a concept of a fish from your language model, and then to go more into details. So now it's a fish, what type of fish? And now maybe if it's a salmon, what type of salmon? Is it wild salmon, a farm? So this is a type of hierarchical structures that I talk about. So we design a sparse autoencoder that takes the activations and try to decompose and at the same time learn these concepts from the data. I'm going to skip the math. So if you're interested in the math, it's going to look into some relations of first, what are the linearly accessible, maybe high-level concepts that I can extract, and then it sequentially move on to concepts that are not linearly accessible. So what this can tell, where this can be useful. So we try to apply this on multimodal text and image large frameworks, a CLIP, that tries to learn representations of multimodal data. Imagine that we have concepts such as a text that is trying to represent text of a zebra, and you have an image of a zebra. So you can have an SAE that is going to repeat itself again, that try to learn a concept of text-specific of zebra and learn a concept of image-specific. But if you were to thinking about it hierarchically, you can extract text-specific first, image-specific, and have a direction that looks into a concept of a zebra. So we looked into how are these shared structures in the clip of the this multimodality encoder offered by OpenAI. And here I'm showing 3 sparse autoencoders, and depending on which one you use, it gives you different properties. The key information is that if you were to focus on the right model, which is the framework that we offered, it is able to find a few concepts that are blue, that is related to the text, for example, a few concepts that are reddish, yellowish, that are related to image modality, and then a lot of mixture of dots that shows that you have subtracted text related, subtracted image related, to really find maybe that information that makes zebra a zebra aside from what modality you have. All right, so this was just a tip of an iceberg about mechanistic interpretability, but now let's go into the second portion of the talk, which tries to maybe design models that can give you things that are valid and respect the laws of the nature. All right. So let's say we master at mechanistic interpretability, and we could fully interpret our AI system. Are we done? I have 29 minutes. I wish I could ask you a question and say, are we done or not? So raise your hand if you think we are done. OK. I should ask the other one, because now I don't know if you're not done. So raise your hand if you think we're not done. OK, we have listeners. All right. So what if I give an image of a husky to my classifier, and it has classified it as a wolf by mistake? And I ask it to explain to me, how did you come up with your decision? So what if it give me this explanation, which means I looked into the snow, wolves, huskies, wolves. So wolves happen with snow. I made spurious correlations. So this is why I'm thinking that there is a wolf. So this is a classic. So I'm showing a maybe not very harmful error here. So, but this is a classic spurious correlation that neural networks or AI systems are not really looking into what makes wolf a wolf. So what are the causal relations that exist? So maybe if you as a human try to interpret, probably you're going to look at the eyes, the features of the ear, so something that is not a spurious correlation that you might have developed. I'll bring another example. So let's get back to that world model. So we all saw that it was doing a perfect prediction of how the planet move around the sun. So this is a work that was done, I think, a few years ago, maybe 3 years ago. So when they were to extract the world model from the foundation model, in terms of the force that exists, how makes the planet move, it gave us very random forces. So it had to, the correct one, hopefully we all passed our second year physics, it actually has to go from the planet to the center, as we're showing it to the figure in the left. So what does this mean? So, and this is even worse with language model, because we tend to bias when someone speaks to us so nicely. So even though these frameworks may do a very good job of predicting something, they may completely rely on a wrong understanding of how the world works. And this might be one of the key challenges of why these frameworks, when you move them to a completely new scenario, they drastically fail, because they did not understand the essence of the general principles that we have in our physical world, how a planet should move. So this basically brings me to the idea of maybe instead of trying for us to spend large amount of money to train these frameworks and then do post-hoc interpretability, we need frameworks that are inherently interpretable to be able to respect some of the laws and constraints that we want them to do. All right, so I'm going to show you a path of how to get there. So this is one approach, and I will be happy to talk with you after the session to hear your thoughts about your approaches. All right, so in order to find where is a key problem, so let's get back to how do we do science, or what do we do in science? There are data, there are experiments. We conduct some experiments, so we observe. And then what do? We go to the task of modeling. So think about it in the case of the neuron. So you basically look into the neurons, and you're trying to find maybe some equivalent of a circuit that try to explain it. And your job in doing that is sometimes to form a hypothesis and to come up with a model that explains the observations that you are seeing. Hopefully we have some scientists in the room. And then what do? We infer. I would like you to take this word with you. We infer based on the model that we have in trying to maybe uncover some of those hidden causes that led us to see what we see. So for example, in the case of the neuroscience, this can be some brain functions. It can be related to what is really in the environment that some neurons are encoding, and such and such. OK, what is the next step? So based on our model and our inference, hopefully our framework is powerful enough such that we generalize it. So what does this mean? Hopefully we have an understanding and a conclusion that is lasting, such that now we can take it from here, maybe a theory that is proposed in 1900, and to apply it in the 21st century. Or maybe to take it from one continent to another and still working. Apply it to a new human. Apply it from one animal to another. So this basically means, so if I want to summarize it in one sentence, so what we're trying to do in science is we're trying to look into some complex phenomena and distill that into simpler frameworks and principles that are generalizable. So what has happened in the age of technology? So what has been the role? So in the early 20th century, technologies helped us to maybe modify how we used to do observation in our scientific experiments. And then a little bit further, we come up with computers that allow us, we maybe move away from pen and papers to move on numerical simulations, algorithms, solving optimizations to help us with the modeling. And then, for a long time, we, as intelligent system, were responsible for the third and the fourth component. So what they are, so let's say inferring is that understanding, and generalizing is those discovering the underlying principles that we're looking for. But unfortunately or fortunately, the AI has tried to automate all the way from modeling in an end-to-end fashion to not go into a sequential way. So they don't do modeling, inferring, generalizing, prediction. They actually take the data and give you a prediction. So it's basically skipping these steps that we were taking to be able to gain a real understanding of what's happening in our data. So this is what you can probably refer to it as it's doing a job of prediction without understanding. All right, so if you would like to know a little bit more about this, so here is an interesting read, 6-minute read, so probably you can read it right after here, on trying to probably explain what I just explained in the last slide with some other words, But one of the codes that exists in this 6-minute read is the fact that we all know that AlphaFold has been doing a really remarkable job in trying to give us new proteins. So, however, it has not been helpful to help us to have some understanding and all the story that I mentioned. So I'm not going to spoil the read that you want to do at 3 p.m. All right, so let me now take you through one approach that tries to look into the modeling and inferring and generalizing inside of a large neural network. So here we designed, I'm not going to go through how we did it, so feel free to take a look into the publication down here. So we designed an interpretable AI that when it tries to analyze the data, it has an inference type of computation inside its module. Another key important thing is that we know a little bit about the data that we want to analyze, and we designed it in a way that it respects some of those inherent structures that we know exist. This is a neuroscience data that we want to learn from about spiking activity, the fact that the animal is exposed to distinct information in the environment sparsely in time, so it's not that it's constantly getting stimulated, and the fact that neurons fire locally. You can take this approach, the general approach, and apply it to your own data with some other form of structures, but here we took sparsity and locality. All right, so before I forgot, actually, this is also a joint work with it several years ago, before I actually joined University of Alberta, with 3 research labs at Harvard University. Again, Valerie, that she should be somewhere in this room, is also part of that job. Hopefully she is in this room. All right, so let me show you 2 neuroscience data where this approach has helped neuroscientists to use AI for gaining their understanding about how that region of the brain that they were trying to study and hopefully to have answer for some of their scientific questions. All right. So we identify some dopamine neurons in the brain, and we try to insert some electrodes to capture activities of those neurons. Disclaimer, I'm not a neuroscientist. I'm making a simplification here. And we collect some data in an experiment. So how does the experiment look like? So each of these dots that you see is a spiking activity from one neuron. And usually the experiment, how it goes is that there is a time component in the x-axis, and there are a series of trials that you repeat that experiment. So in this setting, there are 2 types of experiment. So in one, that the animal was not expecting to get a reward in form of water, and these are dopamine neurons. When you give it a water, it gets excited. So this is why at the onset of an unexpected, you see a lot of activities. And then there were another scenario that called expected, where you kind of, in a reinforcement learning fashion, in an experiment, teach the animal that maybe if I show you something, if I give you some orders, I'm going to give you 1.5 seconds after some reward. So we call this an expected. So what is the goal? So can we use an AI system to give us representation that can distinguish between whether the neural activities are coming from unexpected trials or coming from expected trials, but at the same time characterize these neurons in a way that how much of a reward has been given to the animal and if a reward has been given or not. So there are a few things that you can thinking about that we want to understand. And in this setting, we apply the framework that I showed you before in a way that we learn some localized concepts that give us information about the trial type, and another one give us information about the reward size. So for example, if you focus on the right bottom corner, as a function of a reward size, the amplitude of that representation is increasing as the reward size increases. This is what I'm referring to it as it has encoded how much reward has been given to the animal. So I'm not showing it here, but if you were to indeed apply maybe a large deep learning unstructured framework to fit your neural activity and you were to poke in to try to understand its internal activation, it was not offering you representations that were interpretable in a way that I'm showing you here. All right, another example. So let's say now we take our framework, still a work with neuroscientists, and we want to understand, we place the mice in a relatively naturalistic environment that it can interact with a variety of features in our environment, and we measure calcium signals. So the leader of this research, a neuroscientist, had a hypothesis at hand. So she was trying to understand what are the factors that really one particular type of the neurons are encoding. So, and depending on which region to look into, can you make a statement that this region in the brain is only encoding this information and this other region of the brain encoding that? So how did we tackle the job? So she was looking into two different neuronal types, and then we apply the method in a way that we have a temporal sparse representation that tell us at which time of the experiment there has been some factors that have stimulated the brain, but not only that, we looked into the concept characterization such that it told us a region of the brain is encoding two types of information, which is the first row, and the other region of the brain encoding one type. And indeed, that was some of the hypotheses that she had, that with the help of our framework, we were able to maybe help her to answer her scientific questions better. So if you were to take a black box approach, of course, you can construct autoencoders in a way that you feed in neural activities. At the output, it reconstructed very well, or maybe you feed first 10 seconds of your neural activity and it can predict what comes after. But the job of the prediction or fitting the data is not going to help her to be able to answer this question unless we can extract or maybe have a framework that gives us some form of interpretable representation. So this form of interpretability, I did not go into the details of that. You can also thinking about it, we need to have a neuroscientist perhaps to interpret this with their own language. All right, so in case you were sleeping, so wake up, we're in the last slide. So we talked about two forms of interpretability today. So one, that it's very emerging. A lot of people nowadays talk about it, and indeed there are interesting opportunities both in academia and industry about it, how we can understand large systems such that we identify why they're failing, so that we can maybe explain to our customers why we made a particular decision, or at best, we can mitigate those harmful effects. And the second one, in a way that it's more useful for scientific domains or regions that you really want your AI framework to respect some properties. Maybe you have a conservation of energy in your scientific experiment. Maybe you have a constraint in your budget. You want to make sure that it's never really going to go beyond that if you're using it in a banking system. So an approach that allows you to incorporate a few of these useful properties so that hopefully you can make them more reliable. All right, I would like to now go for questions if you have any, and thanks for listening.
I think this is working.
Yes, I can hear you.
I read the article you shared from Tony Zader last night. It was really good. The blog post that you posted earlier. I'm just curious what you think about whether these models can learn about the world in a way that's grounded in reality, like our knowledge is, if they can't really experiment with the physical world. So, like, can a lot of these models that you're talking about really interact with the world in the way that we do to build knowledge that's grounded in reality? Or can you just kind of show examples of human actions in the world or experimental actions in the world? Is that sufficient to have these models grounded in reality?
So I'm not sure everyone else here. So you all heard the question. Okay. So this is a very good question indeed. So a lot of people nowadays are trying to argue that we need a physical AI. So in a way that it's not enough for us to give a measurements of the interactions that you may have, but you may need some sensing information, variety of them, and touch with the physical world. So my take is that in order for us to maybe make the two forms of interpretability to meet each other is to introduce in a first step some of these structures that we call this interpretable, or some of those way of inferring that I was talking about within these large language models in a first step for us to be able to achieve. But I do agree with you that probably we have a lot of oral community here, so we need these AI systems to interact with the world that they want to understand. And I think we are far from that.
Great, thanks.
Hi, great talk. Thank you for the explanations. I'm a little bit skeptical about the exact statement that the other question, the other person who asked the question did, because I feel like even though we are not bad at making grounded discoveries about the world, I'm skeptical that we can make the claim that that's reality. Maybe we have a very biased way of looking at the world as human beings, and I want to ask, is there a way to distinguish reality from human bias? So, for example, Occam's razor. We tend to like simpler explanations, but you could have a more complicated explanation that is just equally as valid. It makes the same amount of prediction, same amount of generalization. So, are we pushing ourselves towards more human bias, less human bias? Is there a way to account for that? Are we thinking about that? Yeah.
Yeah, thanks for the question. So I think first thing I want to make clear is I try not to mention human interpretable. So I tend to keep talking about interpretability, and that sometimes can mean that we would like to incorporate some mathematical understanding that, again, a human have modeled about the phenomena to be incorporated there. So how I can respond to your question is that all models are wrong. So I do agree with you that we should not really stick to maybe the frameworks that we have been exploring on how we see the world, but the general way of thinking about that, we do like frameworks to go through this, maybe optimizing for some underlying principles. So you mentioned about Occam razor, so that's a very important principle. So maybe we're looking for inherently something that give us an optimized representation with some definitions. And as long as the framework that you develop allow the system to be able to infer and reason about the predictions that they have, I think this is what I refer to as interpretable AI.
So maybe to paraphrase it in one sentence, my understanding of what you said is we're looking for a more principled way of learning representations that corresponds better to inference and logic?
Absolutely.
Thank you so much.
Yes, so if you had saw my talks in other places, so you can think about it that we are trying to do representation learning in a principled way.
Thank you so much.
One more question?
Yeah, thank you so much for the talk. I really enjoyed it. So I'm wondering, when you talk about interpretability, I'm always concerned with evaluation. Like I wonder how, you get a mechanistic idea, and how do you go about evaluating this? And maybe a second part, I'm not even sure if the second part is very related to the first one, but it's still evaluation. So when you show the example of the planets, and then you have like the Newtonian law, and we have our predictions, but then when you look at whatever is extracted from the model, it's like all over the place. Shouldn't we then say that the model is wrong, and then we're just optimizing for the wrong thing? So what are your thoughts on evaluation and these two perspectives?
So regarding the planet that we were discussing, so my statement about that is the model seemed to have not relied on Newtonian or any form of physical model that we have in mind in trying to perform the prediction. So at the moment in the field, we are trying, or let's say the AI researchers are trying to look into the cases that they know the underlying model so that they can evaluate it. And then they are trying to make the statement that if they are following what you think they should, or if they're not, or if they're relying on a similar world model. But if you were to start studying, or if you were to train our large models on maybe a phenomena that we don't know much about, so it would be hard to evaluate it. So we do want first frameworks under known, let's say, scenarios to validate them, so that then when we take them in the wild, we trust what they're telling us about their understanding about the phenomena. So this is how I take it right now for that particular example.
Sounds good. There's also the first part of the question, like if you have a mechanistic idea, how do you go about evaluating it?
Okay, so if I were to do a mechanistic idea how a large model come up to their decision, and then how can I really say that that's interpretable? Is that your question? So it's really hard to say if it's human interpretable or not. So for example, in the case of the language, so they usually try to trace it back to the data domain of sentence structures and to make sense of what they are referring to. So which again means that there is a human involved to be able to see if they're interpretable or not. So, but at the same time, you can thinking about abstract concepts that exist in these representations. Maybe you're looking into data as pure statistics, that there's no human involved, and try to understand them statistically. So that's another way that we can skip the human in the loop. But for industry, I should say we still need human, because we try to use these technologies for the benefit of the society, and we do need expert and human interpretability to make use of mechanistic interpretability part.
Thank you, Bahareh.
Thank you for your question. All right, thanks for listening.